Hello! We introduced strategic games last time. We will now introduce some standard notations for these games and discuss how the best response function can help in finding Nash equilibrium. Now recall that a strategic game is defined by specifying a set of players N, a strategy set Si for every player I, and a utility function for player I, Ui. A strategy profile is a vector S which records what all the players have played. For simplicity, let capital S be the set of all strategy profiles. Now in strategic games, we will often compare the utilities of a player's strategies when we fix the strategies of the remaining players. So we will have a notation for this. Let capital S sub minus I be the set of all strategy profiles of all the players except player I. Essentially, we are dropping Si from the Cartesian product. If S is a strategy profile, then the profile obtained from S by dropping Si is denoted by S sub minus I. And if player I switches their strategy from Si to Si prime, then the new strategy profile is denoted by Si prime followed by S minus I. Now the notation might feel a bit wonky and not really precise, but the notation will make more sense once you get used to it. With this notation, we can now formally define what is a Nash equilibrium. Recall that a Nash equilibrium is a strategy profile where no player is incentivized to switch strategy. So a strategy profile S star is a Nash equilibrium if Ui of S star is greater than or equal to Ui of Si prime S minus I star for all strategies Si prime for player I and for all possible players I. This means that the utility for player I in S star is at least the utility of player I if they switch to any of their own strategies. In the example of the prisoner's dilemma, let's have a look at S star being steal and steal. From player 1's point of view, the utility they get from S star is 10. But if they switch to share, then U1 of share and steal is 0, which is less than the utility of S star. In this notation, the share is S1 prime in the definition, and the steal is S minus 1 star in the definition. We can make a similar calculation for player 2 and conclude that S star is a Nash equilibrium. Let's consider a new game here, the guessing 2/3 average game. In this game, we have 3 players and a positive integer k. Each player will simultaneously pick an integer from 1 to k, and that produces the strategy profile S, which is S1, S2, S3. There is a $1 prize which is split among all the players whose choices are closest to 2/3 of the average of the 3 numbers. The other players get 0. So for example, if S is 5, 2, and 4, then the average is 11/3, and 2/3 of the average is 22/9, which is 2 plus 4/9. Player 2 is the closest, so the utility for player 2 is 1, and the utility for the other 2 players are 0. So is S a Nash equilibrium? And the answer is no. If player 1 switches to 2, then the utility of player 1, when they do that, is now 1/2. And that's because 2/3 of the average is 16/9 in this case, which is closer to 2 than 4. Player 1 and 2 tie, so they each get half. And so, player 1 increases their utility by switching their strategy. Now, what would be a good way to play this game? Is there a Nash equilibrium? Take a few moments to think about this game. Think about whether you should play a number that is low or high. And the idea is that lowering the guess generally pulls the 2/3 average closer to you. So let's try the profile that's 111. If a player switches to, say, T that is at least 2, then the 2/3 of the average is 4 plus 2T over 9, which is 4 over 9 plus 2 over 9T. And you can use arithmetic to check that this is closer to 1 than it is to T. So this is a Nash equilibrium. As an exercise, prove that this is the only Nash equilibrium of this game. Now, one tool that is helpful in finding a Nash equilibrium is the best response function. For a Nash equilibrium, a player does not want to switch. So if you fix the strategies of the remaining players, then you will be playing a strategy that maximizes the utility for yourself. In other words, it is a best response to the fixed strategies. So let's give you a definition here. Player I's best response function for the strategy S minus I of the other players is given by Bi of S minus I, which is the set of all strategies Si prime belonging to player I such that the utility for playing Si prime is at least the utility of playing any strategy Si belonging to player I. So the first part is the utility of a best response, and the second part is the utility of all possible responses to S minus I. For example, in Prisoner's Dilemma, the utility function B1 of share is steal. So when the second player plays share, the utility for player 1 is maximized when they play steal. Similarly, the best response function for player 1 when player 2 plays steal is also just steal. For the 2/3 average game, think about what is the best response function for player 1 when the remaining two players both play 5. And the answer is 1, 2, 3, and 4. And that is because when player 1 plays something less than 5, it will be closer to 2/3 of the average than 5. So they get utility 1. If player 1 plays 5, then their utility is 1/3, as all three players are tied. And if player 1 plays anything greater than 5, the 2/3 average will be closer to 5, so they get utility 0. So the best response among all possible choices is then when x is less than 5. So 1, 2, 3, and 4 are in the best response function. Now, what is the relation between the best response function and Nash equilibrium? Well, if S star is a Nash equilibrium, then each player I must have played a best response to S minus I star. And that is because changing your strategy cannot increase the utility for yourself. The converse is also true. If you have a strategy profile where everyone plays their best response to the remaining players' strategies, then there is no incentive for any player to change their strategies. So it is a Nash equilibrium. And that gives us our lemma here. S star is a Nash equilibrium if and only if Si star is in Bi of S minus I star for all players I. This means that each player plays their best response with respect to the remaining players' strategies. We will leave the formal proof of this as an exercise. Now this lemma helps us find Nash equilibria by looking for strategies in the best response function. Take a look at the prisoner's dilemma one more time. We see that for player 1, the best response to share is steal, and the best response to steal is also steal. So we mark the positions on the table where best responses are played. These are then eligible to be in the Nash equilibrium by our lemma. We can do a similar thing for player 2, and we mark the 2 places where best responses are played. And now we see that for steal and steal, these are best responses to each other. So this is a Nash equilibrium. Let's consider an arbitrary game with the following payoff table. Strategies ABC for player 1, and strategies XYZ for player 2. Now take a few moments to calculate these best response functions for player 1 and player 2, and then figure out what are the Nash equilibria in this case. Let's look at the best response function for player 1. When player 2 plays X, the best response from player 1 is the strategy B, which gets them utility 2. When player 2 plays Y, the best response from player 1 is A. When player 2 plays Z, player 1 has 2 possible best responses, A or C, and we have marked them on the table. And we can make a similar calculation for the best response function for player 2. And we mark the best responses on the table as well. And we see that there are 2 Nash equilibria, and they are Bx and Cz. In each of them, they are the best responses to each other, and the rest of the strategy profiles are not Nash equilibria, as one is not a best response to the other. And we can conclude all these because of the lemma we have above. So that is the best response function. We will look at an example of using the best response function in an economic setting in the next lecture.